I introduce Mr. Matthias. Mr. Matthias was as well a member of board of INEM, the International Network of Environmental Management, for many years, and served as a member of board of trustee of the APRCSP, the Asian Pacific Roundtable of Sustainable Consumption and Cleaner Production. He has worked on the strategic planning group of ISO, International Standard Organization, TC207, and has been member of ISO TC207 and BSI, British Standard Organization Committee on EPE for many years. It's enough. All right. Without further ado, may I invite Mr. Matthias to handle the workshop. Thank you.
Thank you so much for the kind introduction. And yeah, I won this kind of award, greenest person on the planet, some years ago, but I sometimes say, you know, people living in a Malaysian kampung with minimal electricity consumption in one of those nice old houses that uses Mother Nature as a way of cooling rather than air conditioning, they have a lower carbon footprint than I have. So that's always a question of interpretation and perspective. But my passion in life is to live green and to do green business as well. So it's an honor for me here to be here this afternoon. I apologize I'm a little bit late. I kind of mixed up the timing. I thought I was only supposed to be here later on when my name was on the program. But I'm looking forward to share this afternoon with you, learn from all of you, and hopefully help us to have an interactive afternoon where we can learn as much as possible. So I'm a little bit disappointed I missed Dr. Tan. I know he's always got a lot of great practical examples to share, but we've got great speakers coming up. I will summarize the CVs a little bit. I think you have them all in your eco-friendly printed brochures anyway, so I don't necessarily need to read all of the details. We've got the next presentation on passive solar design, the foundation of low energy architecture, by Professor Dato, Dr. Elias, and he holds a diploma in building design from 1969, 2 years after I was born. So he's got so much experience that we can benefit from. He served at UITM from 73 till 1999, then UUM until 2003, and then mandatory retirement, and he served UPM until 2011. And in 2012 he joined UKM, and he holds there the position of Head of Department, Deputy Dean, and was the Dean of the Faculty of Built Environment. And he is the Principal Research Fellow at SERI, Solar Energy Research Institute. Professor Dato, Dr. Elias, we're looking forward for your presentation. Welcome. One big applause.
Thank you, Mr. Matthias. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon. I think I'm quite unfortunate to come after Dr. Tan, after all the interesting ideas, you know. But I think it's, you are fortunate to have him as a speaker. Like Mr. Matthias says, he always has something new up the sleeve, you know. I'm not sure whether I'm fortunate or I'm lucky, because unfortunate or lucky, because Mr. Tan has touched upon some of the aspects that I'm going to deliberate this afternoon. It's more down to us, not those imaginative flying houses or houses on water and so on. So I'll be deliberating on passive solar design, which is the basis or the foundation for low energy architecture, or passive and low energy architecture. Hopefully you are still awake to hear this down to us talk. My talk will be around this framework. I tend to think that passive solar architecture or passive solar design consists of bioclimatic design, which is already known, or which has been researched and more known than the later one. And it is a combination of both bioclimatic design and passive solar systems. I think this is my interpretation of passive solar design. And of course, bioclimatic design for architects, they're familiar with this. It involves understanding of local climate, the environment, the site itself, the context, the site context, which is the climate, the environment, the local features. Those are the climatic aspect, and the bio aspect are the comfort, the human aspect, thermal comfort, visual comfort, auditory comfort, and so on. And the passive solar system will involve the passive cooling, passive solar heating, actually hot water, solar hot water, and daylighting. Those that does not involve any energy input to the system. Passive solar design has a scientific basis from a few areas. Firstly, climate itself, climatology, study of climatology, and then the understanding of heat transfer, thermodynamics, understanding of fluid mechanics, and of course understanding of the human himself, how human behaves, the heat index, psychrometric, and other aspects that relates to the comfort, the human environment. And talking about this passive and low energy architecture, there is an organization that organized annual conference on passive and low energy architecture, PLEA. And maybe some of architects here, those architects will be familiar with this, those architects and planners. But mainly this is based in Europe and South America. Quite seldom it comes to this area, to this region, except for once in 2007, a PLEA conference was organized in Singapore, which I attended. And it happened that the president and the PLEA board secretary are both from AA School of Architecture, where I did my PhD under Simos Yanas himself. But this is a site that I think if you want to know more about low energy and passive architecture, they have got a lot of there's a whole body of knowledge, research, findings, and so on from the conference papers. Go to this site if you want to get more information on this, especially those researchers on this aspect. Okay, just now Dr. Tan talked about the world. We are having population explosion. We are getting 7 billion over. But my talk refers more to the sun itself, the solar, the sun system. The main player is the sun. The sun brings life and warmth, light and warmth to life on Earth, but also it has temper. At the moment, March, every year, March is the hottest year when the sun is overhead for our location, equator. And particularly so this year, I think there's a lot of happening in the sun itself, a lot of solar flare, and there were warnings about the sun, the solar activities as well. So our sun is getting angrier and angrier. And related to this year, I'm not sure whether anybody in the audience who is familiar with this. This is the solar revolution, the feature film that was named the best for this year. And this idea is from a German biophysicist named Dato, who has done research relating to the activities in the sun that can affect not only the planet but also our brain, human brain. Apparently our human brain has got some minute magnetic things that can be affected by the wave that is happening, but the activities on the sun. But it is for the positive side. I have not seen this film myself, but I think I would encourage, I will try to get this for my own viewing, and it sounds very interesting. Okay, passive solar design. There are basically 6 principles that I would try to elaborate on relating to passive solar design. And this actually is available within, or is encapsulated in, is captured within MS 1525, the new one, the revised one, where we were also involved in giving inputs for the passive design. So the first one is to orientate. I think this has been covered by Dr. Tan earlier, so this is a repeat. To orientate, the first strategy is to orientate. The second strategy is to shade. Third strategy is to insulate. Fourth is to ventilate. Fifth is to dilate. And I have added to utilize it, where SE is the solar energy. Utilize the solar energy that is available on your roof, on your site, and on this earth. And among the green ones, you see that the shade, insulate, ventilate, and dilate, these are the factors or the elements that will affect the facade design. The windows, the walls, the openings, the shading device, the glass, and so on. This will be affected. So my presentation will more or less be around these areas. Designing within contextual climate and site are the first steps in the reduction of energy consumption that will result in operational cost saving. So this is from MS 1525, clause 4.1. And in this MS standard, which is being reviewed, there are passive measures, specifically specified there in clause 5 and clause 4 and 5, architectural and passive design strategy, and clause 5, which is building envelope, the walls, the roof, the floors, and so on. And active measures, these are the engineers' area of work which architects will not venture into. But the work always starts with the architect. The design starts with the architect. If the architect makes a mistake, and the engineer will have to come and to address that mistake, it can be costly. So it is highly important that architects or designers who design buildings, they know what they are into. Their decision will affect the long-term costs of maintaining the building, upkeeping. These are just the elaboration on those strategies. Yeah, the first one, appropriate orientation. These are the things that are already familiar. Yeah? So I will go through this, but I will not go into depths in all of them. Only certain aspects I will go into some depths, which I think might be new to some of you. Orientation of the building, especially opening, which should avoid east and west. So Dr. Tan says it should face north and south. It's the same. Improvement of the microclimate. Sometimes we forget about this. Around buildings, immediately just outside the building, the intermediate space between the external and the internal, so that there is a transition. And this can be done by having corridors, having balcony, having terrace, and with plantings and so on. And you have to be careful also not to allow heat from the hot paving, etc., to come into your building. Secondly, is to protect the building from the sun, primarily by shading. This is an important aspect, sometimes taken for granted by many, and sometimes totally neglected or forgotten by some. I will go into slightly more detail on that. The third one is appropriate and adequate choice of the building envelope, material for the building envelope, as well as in the insulation to reduce heat transfer. So as well as to use a surface that is reflective, and surface that have colors that are reflective in terms of the sun receipt. Number 4, removal of the internal heat by natural ventilation. Not only that, but also we have to create air movement so that we can exhaust the space inside, the pollutants, etc., from inside the building to outside. So it's not only the wind coming in for comfort, but also for health, ventilation, air change, air change, constant air change for the interior. Next one is daylighting. Daylighting of building. We have to ensure that we have a evenly distributed daylight. Of course, Dr. Tan just now mentioned about the hall, which use totally daylight. I remember in the early days of Putrajaya, I went to visit. In fact, I went into the hall, one of the hall there, where they had a few holes on the roof, but those are openings to the sky. You can close. I'm not sure whether they actually use it. Those are daylight from the top of the roof. I hope they're still there and they're being used. And such technologies are quite common now, I think, using what we call light tubes, taking the daylight right through, even through the whole floor to the floor below, as though they are column. And this can be done, and of course it will cost some space and some money. The last one is the use of solar energy for heating requirement, and this is a very common thing. Okay, like Dr. Tan mentioned, the world is rotating, it is at a tilt of 23.5 degrees, and because of the tilt, we have variation of position of the sun, throughout the year. Every day the sun comes out from the east, moves up, and then set in the west. But as we move around throughout the year, it moves from the south to the center, to the north, and then back to the center, to the south again. So this is because of the tilt of the earth. And this, we have translated this into what we call solar chart. And this solar chart, for us, we are quite lucky because we are near to the equator. So it is fairly balanced. The number of months the sun is in the northern hemisphere is almost equal to the number of months the sun is in the southern hemisphere. But if we are in London, will be this one will be more like that, It will be down. Whereas in Australia, in the south, it will be more curved outwards. It is due to the position of the location. And traditionally, we use a shadow angle protractor to find the location, the angle of the sun, the position of the sun in terms of vertical and horizontal location. Of course, this is some data about Malaysia. I don't have to go through this. Okay, let's go to the first strategy, orientate. As we said earlier, we try to avoid having to face the east and west, but we cannot avoid having the walls. So we try to avoid the openings. We cannot avoid the roof at all from facing the sun, because the roof is the largest area for a low building. For a high rise, it will be slightly different. For a low building, the roof is the largest area that receives the sun, and therefore it is important to consider insulation, not only to the roof but also to the walls, especially the walls on the west. Okay, orientation. When we say orientation, it's not only the block. We are also talking about the planning, how you locate the rooms. So we have to try to make sure that habitable rooms are not located on the west, because they'll be quite hot. Try to locate toilets, kitchen, store, or lifts, or utility rooms on the west side. And also openings, of course, we want to face north and south, and also openings not only to capture the site, to avoid the sun, but also to capture wind direction. To me, it is important to capture the wind into the house, whereas the sun we can shade. The wind we have no choice. If we can capture it, the better. So the choice between having to capture the sun, the wind, and to avoid the sun, I think I would go for capturing the wind. And then microclimate around building. I mentioned earlier, transition space. There must be transition space from the hot external area, outdoor, into the interior, which is cooler. So this transition will also cool down the interior space. And there are many ways of doing it. You have corridors, you have terrace or balcony, and you have to have landscaping to assist in terms of to absorb the sun rather than keeping the heat that will be blown into the interior. And also you can have water body to, even if it doesn't cool, psychologically the sound of this fountain, will make you feel good, fresh. Okay, strategy. Next strategy is shade. Protection of the building from the sun, primarily by shading. This is earlier on, of course, the same figure. Okay, we have some. What is important here is actually the angles that you have to cover. You have to know in order to avoid the sun hitting your opening or windows. So here we have the horizontal shadow angle and vertical shadow angle for these devices, or how deep these devices should be according to the orientation and what time. So this is just a guide. You can get more accurate one because now we have a lot of programs that can calculate very accurate. But for architects, I think this information is good enough, for you to draw the sunshade, to design the sunshade, depending on the orientation of the opening. Of course, there are many ways. Knowing the angle is one thing, but translating it into the design is another. You can have you can have just a simple slab like that, or you can have a slab that is slightly tilted down, a slab that has got a little bit downturn at the end, or you can have several slabs that can handle the angle. You can have less slabs but more of it. You can have smaller ones, and also you can have the vertical. So these are quite basic thing, quite primary thing that architects learn in the early years, maybe year 1 or year 2, but sometimes it is forgotten in their practice. Okay. Okay, this is actually one of the design for the project in Sarawak. We have taken this to do some exercise in terms of shading, the effect of shading. So we have what we have done here is to have the same plan, a bare house without any shading, a bare house without any shading, a house with just the roof eave, and then another one we have added just a simple horizontal slab. And from the graph you can see that there is a reduction in terms of annual solar gain. So this is just a parametric study just to illustrate the effectiveness of having this shading device. Of course, in Malaysia, one of the best building that I really admire is the planning on the UTP, University Technology Petronas. It has used the right approach, the right tropical design approach, by putting a continuous roof that acts like an umbrella for the whole complex, and then you can move around under it. You can bring the daylight, but the rain also will come in. some places. One of our problem here is the rain. We want to have daylight, we want to have ventilation, we have to louvers. Then the rain comes, then we start closing all the louvers. The same thing happened to my house. When I designed it, there were a lot of louvers, but it was on a slightly high ground, so the rain comes with the wind. So eventually I had to close some of the louvers, partially close, and it was less effective when you close those louvers. So this is one example. Of course, this was by Norman Foster. But so even a non-local architect, they are sensitive to the design of the local context. So they have actually addressed it correctly to me. Okay, the next strategy is to insulate. This aspect maybe I'm taking slightly longer because I feel there are some misconception in terms of insulation. Building material themselves are insulation, but sometimes they are not enough. We need extra insulation even to the walls, but especially so to the roof for low-rise building. Okay, this is just some concept about how to deal with heat. We have heat sources, we have heat sink. The heat sources are the sun itself, the air, and the activities in the internal area of the house. And the heat sink, so the sky, the air, and the earth. And we have the mode of transfer, of heat transfer: conduction, convection, radiation, evaporation as well. Evaporation is seldom, normally we will talk about the three aspects: conduction, convection, radiation. Evaporation is less discussed. So we want to avoid heat gain. So we want to discourage the heat flow from air by conduction into the interior, from the sun into the interior, and also heat develop inside. And we want to encourage heat loss from the interior to the sky, from the interior to the air, from the interior to the earth. These are the heat sinks. This is just a basic concept. And this is something that maybe I would like to make a point. Almost all of us are quite unclear sometimes that the most important heat transfer mode is the radiation, as far as house or low-rise building is concerned. Because of the three heat transfer mode, radiation takes up about 87% of the heat that is contributing to the interior of the house. And the heat in the roof is always very high if you do not handle it properly. It can go up to 57 degrees, definitely over 40. And this is where sometimes the correct insulation will make a difference. This is the way the mode works. Conduction will be horizontally through the material. It must have a material. It must have a medium, or carrier. Convection will occur from bottom to up. It's a flow of air. Hot air rises, it brings the heat. Cool air down there, and then hot air rises. But radiation is a surface to surface thing. From hot surface to the cold side. So this is something, it doesn't affect the air. Sometimes we are in a room or in a building, and the air temperature we measure is equal to the outside. But then we feel warmer. We don't realize it. The air temperature doesn't change because of radiation. Because radiation affects surface. The ceiling surface will hit our skin surface, and our skin surface normally is lower than the ceiling surface, and that's the problem. It's a bahang. It's just like when we are having a campfire or bakar lemang and so on. The fire, that's the source of heat. Its temperature is higher than our skin temperature, so we will receive the heat from the fire. Or let's say when we are playing golf, for instance, we are in the sun. As soon as we go under a tree, we feel cool, or anywhere for that matter. When under a very shiny day, on a sunny day, as soon as we go under a tree, then we feel very cool. Why? Of course, we do not get the sun. But why does it feel cooler? It's because our skin temperature is higher than the leaf temperature. So we are radiating the heat in reverse. Just now we are receiving from the sun. We feel very hot. But now under a tree, very cooling. and with some breeze is even better. So that is the concept of radiation. So as I said, both conduction and convection transfer needs a carrier or medium. Only radiation heat transfer can occur even in a vacuum. Of course, it can occur in air, but it can occur in a vacuum. Okay, the point here is the E value, emissivity here. The radiant heat is invisible and has no temperature, it has just energy. When this energy strikes another surface, it is absorbed and increases the temperature of that surface. The emissivity, the E value, just now we mentioned low E value and so on. The emissivity of the surface determines the absorption and also the emission. We'll see later on what it means. Okay, maybe this diagram illustrates well. The sun hits a black surface, so only 0.03 of it is reflected, but 0.97 is absorbed. But at the same time, this black material can emit 0.97 of energy quickly, so because it is black. Whereas the other one, the silver coated block, it will reflect 0.9 of the energy and absorb only 0.1, and likewise it will only emit 0.1. So the emissivity is very low. So this is the properties related to emissivity. So when we say low E value for glass, so it's having a property similar to this silver coated block. This graph illustrates a typical trend of heat flow. It's just another way of showing the relative importance of the three modes of heat transfer. This is in summer or in hot condition, whereas this one is in cold condition. In cold condition, the heat loss is in the reverse. The heat is lost more by convection. Of course, there is also some radiation loss there. And we go on to thermal insulation. Thermal insulation, there are two types. One is mass or bulk, which has got material density. The other one is the sheet, the reflective insulation. Of course, insulation we need throughout the building, even the walls, the walls, not only the roof, the walls, and even the floors. These are bulk or the mass insulation examples. And this is an example of the reflective insulation, lightweight, weatherproof roll form with the bubble. Okay, the major difference between mass insulation and reflective insulation, as far as property is concerned, is that in mass insulation, the R value, the resistance value, depends on K value of the material plus the thickness of the material. Whereas the R value for reflective insulation depends on the surface emissivity and the air cavity that is trapped within two reflective surfaces. And there is an important difference here when we talk about aluminium or reflective insulation. One is called reflective insulation, the other one is called radiant barrier. I was confused myself earlier on. I always took it that they are the same thing, but they are not the same. They are different. One has got R value and the other one do not have R value. So the one is called reflective insulation is defined as one that is having more reflective air spaces, having one or more reflective air spaces in a closed situation. That means unventilated. Whereas the other one is just a radiant barrier, defined as having a shiny surface that is facing an open airspace. And this is typically installed in the attics, let's say on the ceiling, and facing up and so on. And this do not carry any R value. And this is the confusion that has arisen in terms of calculation and so on. But all is down to the K value of the material. Here it starts with the K value of the material. You see the air is 0.02, or polyurethane is even better, 0.021. Whereas granite, your road and so on, 0.22. In fact, your road, our roads, is a very, very good solar panel. If we can harness the heat that is captured in the road, imagine our highways, we can have a lot of electricity, or even heat, thermal energy, which can be convert into electricity as well. So, but there are some research being done into this. So some other materials, you can see water 0.66, wood 0.1, straw board 0.09, and so on. So this is the basic property that will determine the R value and eventually the U value that is used for heat calculation in buildings. So the key properties, the R value is actually 1/K multiplied by the thickness of the material itself, and the U value of the whole assembly, it is calculated as the cumulative resistances from even the external surface to the internal surface, and that is the U value, that is calculation. But of course this is quite boring. Okay, reflective technology has been used by NASA and so on, of course, to avoid the intense heat from the sun. These are some of the advantages and so on compared to mesh insulation. Basically, the most effective kind of reflective insulation is this type in terms of concept. It's got two reflective surfaces, which has got low E, as I mentioned earlier, and then in between we have got the air that has got low K value. So the whole assemble is an insulation and it has R value. So this is just a concept like our thermos plus low E properties. Okay, no heat, but to me it's still, we do not neglect, we do not just put away our mesh insulation. If we can use both together, a combination of reflective and mesh insulation, especially for metal roof, where we need also to consider noise. To dampen the noise, we need the fiberglass or rock wool and so on. So it is best that we combine the two in certain circumstances, but in some circumstances, under other circumstances, it can be on its own. So another one that is related to earlier on, aluminum foil. Aluminum foil is just a sheet. The sheet itself is not insulation. It has to come with air. So if we just use the aluminum foil on top of our roof, you will not get the effect of the radiation. You will not get the reduction in terms of heat from the roof. You have to have two sheets of aluminum, and in between you have to have the air, which is not ventilated. Then that assembly has got R value. Otherwise, it's just aluminum foil. These are some of the uses. Just an example. Okay, the next one. How much longer, Mr. Matthias? Okay.
Still have
Plenty of time. Okay. Okay, the next one is ventilate. Ventilate is to remove the internal heat by natural ventilation, and also to increase the air movement indoor. 10 minutes, okay. Okay, this is my observation, and maybe many of us. Most Malaysian residential buildings are designed with air conditioning in mind. I think when they design it, they have air conditioning already, because it's quite cheap, very, very cheap. And we notice that there are minimum openings or non-operable openings provided, and these are mainly for daylight and view. So like Dr. Tan mentioned earlier, we need, he was mentioning about operable, we can close and open. The best is to have permanent opening, but of course at times we need to close, so we need to provide what Dr. Tan mentioned earlier, openings in the building that can be operable, because some houses they have fixed glass, They have opening but fixed. You cannot open at all. We come to that afterwards. There's one house there. And because of this, the house looks to us suffocating. They just have just a small window for opening. There's nothing else. And we are just wondering, how is the indoor air condition, indoor air quality in these houses? The aircon, okay. But what about the quality itself? Unlike, I think, in some traditional houses, especially in Indonesia, even the traditional houses, they have above the doors or above the windows, they always have openings. If you notice that, and that is very important. And this is why I have this. Okay, we go to this. This is called the Cool Tech Energy Efficient Home by Stephanie and Harry Boswell in Malacca. We were informed that Mr. Harry passed away last December. Harry Boswell. So unfortunate. And in all the presentation, they have been talking about the energy save. But of course, this aircon 24 hours a day. They use cool air under the earth. In the earth, they have also a system to keep it cool. So they spend, I'm not sure, about 2 ringgit per month, I think, to run the aircon, because they insulate, fully insulate. The windows are fixed. You cannot open the windows. It's fully insulated. Therefore, once it's cool, it's just like a fridge. You can keep the coolness there because of the foolproof insulation. But I'm just wondering, what about the air quality, indoor air quality? Whether anybody has mentioned it. I have not been there myself, but I think it's something to learn from. Okay, that is why I have taken this house, this Malay traditional house. You mentioned earlier you would like to be in such a house. If we can learn from this house, you look at the way the openings are provided for the house. Of course, it's on stilts, but it has got openings there. Of course, the windows and so on, opening up there. I think throughout, that is something which maybe we can learn, we can provide in some ways. The principle is there, but how we translate into modern design is something else. So I have lived in similar house to this, like this, and at night it can be very, very cold, because of the radiation to the sky. Depending on the roof type, some are just zinc or aluminum roof without any insulation, so it can get very hot. But under if we use even newspaper or anything to prevent the heat from, it's effective. So ceiling and so on. But this house, also this illustration shows us the principle, the basic principle of good ventilation in our traditional Malay house. Again, for a large space, in this case is mosque, it is handled differently. The ventilation is through a stacked roof, from the top from the top of the roof. It's purely for ventilation, but not for lighting. You see, this is something that is lacking in terms of our traditional house. Good in ventilation, but quite poor in terms of daylighting. It's quite dark inside. Of course, this is a new design somewhere in the US, I think. No, in Panama, Tropical Research Institute. Okay, talking about ventilation, apart from depending on the natural ventilation, we can also enhance the natural ventilation using some phenomena. In this case, we can try to use the Venturi effect to somehow encourage higher speed of air through some means. And also, there is another one which is called stack effect, buoyancy, depending on the density of the air. And this can be used in the chimney, and also in air well or in atriums. And of course, there are some local research, maybe a lot of local research being done in terms of field measurement, field experiments. Wind tunnel modeling, I'm not so sure, but nowadays they tend to go more for CFD, computational fluid dynamic simulation. Okay, this is one of the experiments done both for field experiment as well as CFD at UKM, where we are trying to find out using Venturi effect how much that can enhance the airflow. So this is still being carried out and it's not finished yet. So it will be interesting to see the end result. And there's another one that has been done early on. This is completed. It's using a combination of chimney. This principle was used in the is it zero energy building? Zero building, or the earlier one, the first one, Keta, in the center of the building, but not quite successful. So what is being done here is that the researcher is trying to combine the concept of solar panel there to heat up this place, so that there's a hot air that will rise to give a more temperature difference between this area and that area. So buoyancy depends on density of the air, and the higher the difference, the better the flow. So there was some good results, and this she applied to a single story shop house, of course by simulation. The first one, she did some experiment to find out the configuration of the chimney and the panel, which is the roof actually, just paint it black and with a glass over it, to create that kind of high temperature to move the air, and then to find out the effect at the end, at the top. How it should be configured. Of course, she also did simulation, also about the shading, which orientation of the panel would be the best. And then she concluded that it is viable. Now, of course, this is an experiment. We need to do more research in order to make it really applicable. And she has applied it to the shop house. Okay, the next one is on daylighting, daylit. I will not go too much in this. Yeah, okay. Yeah, just okay, daylighting, again, as I mentioned, our traditional houses are not really good. It's lacking in terms of day house. Good in ventilation. We have this available daylight, and then these are the ways, many ways. There are a lot of information on this. We can use shelves, daylight, light shelf, as in the geo building. And of course, as I mentioned earlier, we can use light pipes now, light pipes where we cannot get it easily to the top. And in terms of solar energy, we have the familiar photovoltaic for household appliances, lighting and so on. And we have the solar thermal for hot water, solar cooker even. We are doing some work on this. And of course, now some people are developing PV and thermal, one panel that can do both. You can have electricity, you can have hot water, or even 3-in-1. The roof, the whole composite can be the roof product itself, and so you don't have to buy any tile or metal roof. So this is being looked at. This is the normal household electricity consumption. This is the breakdown. Of course, this is the principle. If the earlier we tackle this problem, the less we spend. If we leave it too late, then in terms of the cost, it will be much higher later on. So to architects and designers, please use passive means of design to avoid creating design problems that need to be solved by engineers and so on, by active means, and also by maybe expensive technologies. So thank you very much.
Thank you so much, Prof. Elias, for a fascinating presentation. Wow. I thought some of these aspects of, passive cooling, insulation, was quite simple, but when I saw all of these big calculations, I was wondering, is this something only professors can understand? But then on the other hand, did the Kampung people get it right when they followed their intuition? Where are the trees? Where is the wind? Where is the right positioning of the building? So I'm sure there are some questions from the audience. I definitely have some. So this is your opportunity to get more down to the nitty-gritty of how we can get it right in our projects, in our houses. What are the best solutions? Fascinating stuff. The audience, yeah. There is ladies first.
Assalamualaikum, Prof. And very good afternoon to all of you. I'm from UITM. My name is Rabiatu Adawiya Nasir. Actually, my study is about adaptation of thermal comfort in outdoor condition. I understand thermal load and heat transfer is more in hot and humid condition, especially in Malaysia, than in other type of climate, colder climate, I mean. Just in case, if Prof can share with us, I would like to know whether the implementation or the application of this passive low energy architecture or building, I want to know whether how far the building being adapted by the residents or the user in the range of so-called comfortable condition. Are they comfortable enough, or they still need the improvisation? Thank you.
Okay, thank you very much. We need a survey to answer that. Because, I think thermal comfort is very personal. Also, it depends on, because thermal comfort depends on air temperature, mean radiant temperature, which is, mean radiant temperature is caused by the radiation, and humidity, airflow, activity, metabolism, and the clothing that you wear. So, personal factors do affect, apart from what they are given, the environment they are in. So I'm sure even in thermal comfort index, they have a adaptive index. They call it adaptive index. People adjust to situation. So to answer your question, yes, I think in terms of thermal comfort, people do adjust, and sometimes they even change the environment to suit themselves. So sometimes what we can design, architects can do is to plan, but in actual fact, the occupants themselves would be the ones who would know better, And in this case, I think a lot of our so-called low-cost houses, nobody really talks about comfort. They talk about how low they can go to sell those houses. How cheap those houses will cost. Nobody talk about comfort. I was just wondering why. Yeah.
I think you're absolutely right on that. I mean, low-cost houses are built the Western style, and then you create a social problem because it's so hot inside that the youngsters are loitering outside because it's uncomfortable inside, and it's too costly to run the aircon. Is actually a tragedy, I think, the way we have built low-cost houses in this part of the world, where we should have learned from the traditional way of building houses. Instead, it's just been the standard Western style, which doesn't really work.
Does that answer? Okay, thank you.
Okay, next question. I can see the gentleman there in the front. Maybe you can you get out there, or shall I come over with the microphone? Let me come over to you. No worries, you're stuck there in the chair. Oh yeah, this man has got a strong voice.
Yeah, good afternoon.
Afternoon.
My name is Robert Pascoe. I'm from Canada. I do a lot of research in the types of technologies you're talking about. I'm just wondering if your institute has done any research into thermal coatings, ceramic type coatings, or other types of thermal coatings, or any testing in that area?
Oh, not in our place.
No?
Not in our place. I'm not sure in UITM, do you have that? Or other institutions? Clothing. Yeah.
Coatings.
Oh, coatings.
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 Thermal coating, like paint.
Oh, sorry. I thought clothing.
Actually, cementitious type
Coating,
coatings.
coating,
for,
yeah. Okay.
Yeah. to
Not
replace
in our
insulation.
place, yeah.
No? Okay.
No.
Well, then maybe we should talk later. There's very interesting technology.
Yeah, I know one of my friends is selling one of those ceramic roof coatings, and he was struggling with sales 2 years ago, but it's starting to pick up now because I think people are realizing that you can massively reduce the temperature, especially on a roof. And if you have white color, reflective color, you know, especially the radiation thing.
Yeah.
I mean, that was one thing that I wasn't so clear on, I have to admit, that radiation is actually the main thing. And I wanted to ask you, the typical aerated concrete blocks that people use for house walls, and I have one example like that later on, does that prevent the radiation, or is it actually an insulation, or is it a bit of both?
It doesn't prevent radiation, you know. Definitely it will absorb the heat. It acts as a sink, I think, heat sink. But it also releases earlier.
But how come it reduces the temperature inside quite substantially?
Because of the air, the air inside, yeah.
Okay,
Inside,
okay,
yeah.
interesting. Okay, any other questions from the audience? Now I have one more. I'm kind of wondering now, how can we make this practically happen in our construction projects? The knowledge is there, the science is there, there is traditional experience, and just as an anecdotal evidence, I once visited an Orang Asli village in Raup, and you know, the modern Orang Asli houses with the tinned metal roof and the concrete, they were hot like crazy. I was inside one and I was sweating. But the other one, the old style, that one that had not been going with modern developments, with the natural roof and the stills, that was nice and cool. So something is wrong. I mean, how come we are getting modern and we are eliminating the things that have worked in the past? And as we just said, the high rises, the low cost houses, there is so many mistakes being done that locks up hot, high energy consumption residential and commercial buildings. How can we avoid those mistakes?
Yeah. This is I think the responsibility of those agencies, I think, that are responsible for the housing of these people or the welfare of these people. I think to look at whether their house or where they live is conducive, you know. Conducive.
But that would mainly be applicable to the low-cost housing now. But I mean, even talking about residential housing, I went the other day to a show house. I won't mention the name. I asked the salesperson there, so what are the green features of your new development? Oh, no, don't need. Malaysia customers don't ask for it. We don't have anything. I said, really? Wow. So, you know, is there a lack of customer demand? Are end consumers not asking for it? Do they not understand the difference between a cool building where you have thermal comfort without needing to switch your aircon on? I put a provocative statement 3 days ago on my Facebook page saying green living is cheaper. Most people think green living is expensive. And I just used an example. I just booked I'm running a workshop in Penang on Thursday. I just booked very cheap and cheerful Tune Hotel. And I booked it without the aircon package, without the toiletry package, without anything, just the bare minimum. And I have done that before. I just open up the windows, you know, let fresh air in before I start sleeping, use the fan, job done. I don't need aircon. It works. So, but other people are saying, oh, cannot, you know, it will be too hot, will be too sweaty. So, you know, how are we going to make it happen? I mean, is there a lack of demand? Is there a lack of awareness?
I think of both. I think awareness is of course one of them. Awareness, even professionals also. I think they do like some understanding of these materials.
Okay. Yeah, I will come back in my talk later on two other points that you mentioned. One point was indoor air quality. I've been as well at the house of Harry and Stephanie in Malacca. I've been as well at your SERI building in Bangi.
Yeah.
So I have a comment on air quality for later. And I have a comment as well. You made a very important point, architects and engineers, their involvement and their awareness. Usually what happens is they do their job, then a developer wants to go green to get a certificate or something like that, then add on. Add on is always expensive. That's why everybody now thinks green building means expensive building. But if you would address it up front, learn from those passive solutions, you could actually maybe even lower the cost. And I have an example of a building like that massively lowered the cost of construction by radically going green. And that is quite new because most people think green building equivalent to expensive building. So, but I'll give that example later on when I have my talk. So, any final question for Prof? Can we get hold of your presentation slides? There was a lot of good content in there. Wow, wow. Yeah, I would like to get a copy of that, definitely. I think the organizer, it's in the CD. Okay, great, wonderful.
It's in the computer.
I'm looking forward to study your good stuff a little bit more in my free time. Thank you so much, Professor. He deserves a big round of applause for a great presentation. Thank you.